Hi everyone, and welcome to another of Ian's interviews. We've all been wondering what's happening with process node technology. Are we at a fundamental limit? If we look at the roadmaps of the leading process technology manufacturers today, they'll tell you that they've got roadmaps going out on and on and on. So the question is Moore's law dead or is it still alive? We've seen the advent of chiplets and integrated packaging become this new wave of AI technology to enable what is going to be the future of compute, whether that's high-performance computing, machine learning, automotive, or everything else. Joining me today is Dr. Kevin Zhang, SVP of TSMC, a well-known, well-regarded industry veteran. Thank you for joining me on the channel.
Pleasure.
So my first question is that if I go and look at some CEOs giving presentations, they talk about how Moore's law is dead. The fact that they have to innovate on architecture because they're not getting much from packaging and process node technologies. I speak to other people and they say, oh no, Moore's law is still alive. We've got roadmaps to 2036. Where's TSMC's position on this?
Well, I think my simple answer is I don't care. As long as we can continue to drive the technology scaling, I don't care Moore's law is live or dead. But reality is lots of people narrowly define Moore's law based on two-dimensional scaling. That's no longer the case. If you look at the innovation hype in our industry, we actually continue to find a different way to integrate more function, more capability into the small form factor, continue to achieve higher level performance and a higher level of power efficiency. So from that perspective, I think Moore's law or technology scaling will continue. We will continue to innovate to carry the industry forward.
So should we redefine Moore's law? Should we have a new law?
That I leave somebody else to define. Yeah.
So TSMC is known for being very incremental with its process node updates. You'll have a major process node and then minor variations that iterate on a theme to improve power performance density before jumping forward with a new family of process nodes. How much of TSMC's success would you attribute to this incremental strategy? Because we're seeing foundries do both, right? We're seeing foundries do both, the big jumps, and we've got a couple of big jumps coming up in the industry. But TSMC seems very adamant on this, sort of slower cadence.
Well, I don't particularly like the word incremental. If you look at our technology roadmap, from 5 nanometer to 3 nanometer, now first 3 nanometer to 2 nanometer. If you look at energy efficient improvement, it's not incremental, over 30% per generation. But in between the major node, we are continue to drive the incremental enhancement. The reason we do that is we allow our customer to continue to harvest each new generation of technology in terms of scaling benefit. So between the major node, yes, we continue to drive the incremental, but between the major node, actually the enhancement or the power performance density improvement is very substantial.
So is that because when a customer goes into a major node, they obviously have a lot of upfront costs to develop the chip, yes, and then using those updates to that major node, they can leverage the similar or at least similar designs rather than spending a big bucket of money?
Correct. For example, 5 nanometer, right? After our customer migrate to 5 nanometer, they can continue to leverage the incremental enhancement from N5 to N5P. When you get the performance boost, then you go to N4, N4P, you can further density improvement. So those incremental enhancement after you jump on the major node allow our customer continue to harvest the scaling benefits and the investment they make upfront.
So how many of those sort of enhancements to a major node end up coming from, internal, outbound design versus inbound customer demand? Do you end up, having a customer saying, I need you to do this. Can you do it on this process node? And then having to go solve that.
Well, we work very closely with our customer to pick the right technology node to intercept their product. This is often based on specific product design to see where they can most achieve their optimum device level, the product level benefit. So we work very closely with our customer to make the right choice. Yeah.
Have you had any surprising requests from customers?
No, we don't want to surprise customer. We actually work very closely, very open with our customer to make sure they choose the right technology. Remember, we are in a foundry business model. Our goal is really to help customer to achieve successful product. My boss often tell me, Kevin, we are in the foundry business. We work together, we achieve success, but there is a sequence. Customer has to succeed first, then we can be successful.
Okay, so to that point, we're here at TSMC's EU Tech Symposium. You've just had the US symposium, and there's a few going around the world.
Yeah.
And the major announcement, or the two major announcements, I guess, is a new major node, A16, and this new super power rail technology also coming in with that generation. What do these bring to the table?
Yeah, so A16 is a major technology enhancement. Revolutionary in terms of bringing further power performance to future high performance application, especially targeting for HPC and AI. A16 feature nanosheet transistor, which is the industry leading most advanced transistor architecture. But at the same time, we add a very innovative backside power rail design. This backside power rail design allow a customer to move the power supply routing from the front to the back, opened up the space, allow to enhance the performance, same times improve the power supply. This is particularly important for very high performance system design because power delivery has become very, very important and critical. We talk about in a small form factor, you have to bring close to a few hundred watts. So the IR droop become very, very significant. By moving the power rail to the backside, you actually significantly improve the integrity of the power supply rail. Our approach is very different from the conventional design. The conventional backside power rail, basically you just drill a hole, connect the backside metal to the front side of metal. You burn space, right? You have to enlarge the footprint of the library cell. But in our design, we have very innovative approach. Essentially, we move the contact of transistor, the source of the transistor, to the back, without changing the footprint of the library cell. So this clever way allows us to maintain the footprint, provide the maximum flexibility to our customers.
Does that mean that the traditional manufacturing steps go a little bit out of order in order to enable that?
I don't want to get into the specific process step because our RD team will not be very happy. Yeah.
But it is very much, a sandwich design, transistors, signal, power. Surely that would add a lot of cost to the manufacturing.
Definitely will have a cost associated with. But if you look at the density, power, performance benefit, I think it outweighs the cost. This is particularly important for HPC and AI application where energy efficient compute is the king, is the driver. Yeah.
So if somebody goes forward and chooses the A16 node, do they have to take the super power rail with it?
A16, by definition, will have the backside power, so we call super power rail.
Yeah.
Yes. Yeah.
Okay, that's good.
But we do offer the technology option, allow a customer continue to leverage the existing design collateral, don't have to use the backside power. For example, for mobile application, where the power supply, power routing is not as intense, you don't have to use the backside power rail.
So normally at these events, whether it's you or your competitors, the announcement comes a few years before production. So where in the timeline are we expecting A16 and super rail?
We're targeting second half of 2026 going into production for our A16.
For the lead customers and
yes.
So does that mean you're sort of like version 0.1 in the PDK right now, or how does that work?
Well, don't think I want to get into detail into a collateral schedule, but in general, our collateral schedule is designed to target the customer production days. Introduction, as we said earlier, we target A16 going to production by second half of 2026. So our collateral schedule will support that kind of schedule.
And we're expecting this all to be manufactured in Taiwan, in Hsinchu.
A16 will start in Taiwan.
Yeah. One of the other announcements at the show is actually something I find really impressive, because last year you introduced this term called FinFlex, the ability to take N3 and sort of reduce the fin depopulation to decide whether you wanted high performance or high efficiency. And now you're doing this NanoFlex with N2. And FinFlex, NanoFlex, is quite easy to see where you got the name from. But how does NanoFlex differ to what we understand with FinFlex?
Yes, this is a very innovative approach. You probably heard about design technology co-optimization. DTCO. This is where we continue to drive the collaboration between design and technology in order to further optimize our technology offering to provide a better scaling benefit. So FinFlex, you mentioned earlier, because in a fin transistor architecture, the number of fin is digitized. So in the past, before this innovative FinFlex approach, you have to use either 3-fin or 4-fin. You can't swap them easily. So our FinFlex technology at the 3 nanometer allow designer to mix and match different fin based library design. But for the nano sheet, we call NanoFlex. This is effectively similar idea, allow the designer to mix match different height of the library. Different sheet width based on the library sheet width. So you can alternate different size, different height of library, allow design to choose and pick based on specific design target to achieve optimum benefit in terms of power, performance, and the density. Very innovative approach.
So it's still 3 sheets high, which seems to be an industry standard for.
Yes, but you can vary the sheet width, which determine the height of the library.
Then that obviously means you have different VT characteristics based on what you're deciding.
That's on top. That's orthogonal to the height of the library.
So you can go NanoFlex and VT.
Yes. You do have a lot of options as a designer.
You're going to give too many options out, I think, to these people.
That could be a problem.
Pivoting from that onto packaging, I'd be remiss if I didn't mention the fact that TSMC right now, I can't mention packaging without saying TSMC CoWoS in the same sentence. People get mad if I don't say CoWoS. And I know CoWoS is in high demand. We only have to look at NVIDIA, AMD, Intel, or look at the broadsheets to see that this is being talked about actively in terms of where you guys are on being able to supply what the market needs. How is expansion of CoWoS progressing?
First thing first, CoWoS today is the workhorse for AI accelerator. If you look at all the AI accelerator design, pretty much today they all based on TSMC 5 nanometer or 4 nanometer technology plus CoWoS. CoWoS is in high demand. Everybody can spell CoWoS these days. Even the TV reporter can do that. So obviously last year, the AI surge took a lot of people, including ourselves, by surprise. The CoWoS demand has surged tremendously over last year. We are rapidly expanding our CoWoS capacity now. I think the CAGR we're talking about well about 60%. It's very, very high, but still the demand continue to grow. We work with very closely with our customer to make sure we provide their most critical need. But that's the capacity side. CoWoS, in terms of capability, we're also expanding our CoWoS capability. If you look at today's state-of-art AI accelerator, the CoWoS interposer size is roughly about 3x of the reticle size. Reticle size is about 800 millimeters square. So that provide the capability to integrate a full reticle size SoC along with up to 8 HBM. But in the future, just 2 years from now, we will have the ability to expand the interposer size to 4.5x of the reticle size, allow our customer to integrate up to 12 HBM. We're not going to stop there. Our R&D team already started expanding the CoWoS interposer size beyond that to 7 or 8x of the reticle size. So very exciting area. Yeah.
Is 12 HBMs enough? I keep hearing that people want more.
People want more. So that's actually this symposium. We also announced another innovative system-level integration technology we call System-on-Wafer. Essentially, you think about it, the maximum size you can do in a wafer processing facility is a wafer. It's a 300 millimeter wafer. So we take the wafer as our base layer. We can bring all the logic and the high bandwidth DRAM together to integrate along the wafer, the whole wafer area. So this, if you measure using CoWoS term, the number of x of interposer size, it is factually give you 40x of the interposer size. So humongous. So this is really provide our customer to continue to integrate more compute function, more memory bandwidth to address future AI requirements.
So, speaking to that sort of wafer scale, it's very well known that there are two main companies looking at wafer scale today, and they both use you. It's how much do you assist with the customers on, say, when it comes to cooling and power management on that side? Does TSMC do any of that?
We work very closely with the customer. So we do wafer level integration, and the customer obviously have to design the back end, the system level, in terms of how to bring the cooling into the system. It obviously involves lots of collaboration. We work very closely with our customer and the system provider to basically work together to find the optimal thermal solution.
So this System-on-Wafer, it's due 2026, 27?
Well, we already have a limited production, but in the future, as you pointed out, there are going to be more AI high performance customer want to leverage that level of integration to address their future needs. Yeah.
And I do have to ask, you're speaking about 3x reticle, 4.5 times and 40 times. In the future, when reticle sizes have to get smaller due to the technology, are we going to be saying, are we going to have to double that number?
I hope we don't have to reduce the reticle size because what we see is people want to integrate more function closely together. Yeah.
So does this mean when we're going, getting more efficient process node technology, the demand for compute power is always increasing? We've now got wafer scale level packaging. Where's the limit?
Sky's the limit.
Sky's the limit.
I think we'll continue to see the trend. The demand for energy efficient compute is just insatiable, right? We're talking about the AI model, ChatGPT model. ChatGPT 4 already use a trailing variable. In the future, even more. So think about the computation requirement. It's amazing. So we continue to expand our capability. Transistor level, obviously, we have 3 nanometer. Next year, we're going to 2 nanometer. Then we have A16. We continue to drive the energy efficient compute at the transistor level. Same time, we talk about CoWoS, expand, and the wafer level integration. I think putting all this together, by the way, we also bring the optical signaling into the package, right? So putting all this together, really we're talking about provide customer a platform, allow them to integrate more compute function, more memory bandwidth altogether to address the future AI requirements.
So it's interesting you brought up optical because I've actually had a new customer come on board who's optical, and for some reason, suddenly all these optical companies want to speak to me about their optical solutions and about the future of how that applies in high performance compute, but also machine learning. Usually when I speak to those companies, they're dealing with your competitors on the optical side. But you guys have been doing optical for a while, and you've got this new technology. I want to call it COUPE because I'm British, but Americans call it a COUPE. COUPE. So
It's compact universal optical engine. Yeah, stand for. That's how COUPE stand for. Yeah. So we have been doing silicon photonics for quite some time. Actually, we fabricate components, and our customer put the silicon photonics together with the electrical transceiver to form the so-called optical pluggable transceiver. Has been widely used in data center. But what we're doing today is we take one step further, leveraging our most advanced 3D stacking technology we call SOIC, essentially using the hybrid bond technique to bring the electronic die and the photonic die closer together to form a small form factor optical engine. That's where you basically do the electron to photon conversion. We know electron is good at compute, but photon is better when you talk about the signaling. So by building this compact optical engine, then we integrate it into the advanced packaging, whether it's today's probably it's the substrate, in the future could leverage something like a CoWoS to bring them together to significantly improve the bandwidth and power efficiency. If you look at today's pure copper all electronic system, the switch, 50 terabit switch, it burned over 2,000 watts. By using this tiny small form factor optical engine, we actually can bring the power down by at least 40%. So this is very, very efficient in terms of achieve high data bandwidth at the lowest possible power.
So you'll end up with some customers who want wafer scale and some who want to go optical and...
Yeah, I think the key is to bring them together because the compute, it still has to be done by electron.
Yeah. So in that space, I do see some companies talking about, because you're talking about having two separate chips, the electrical and the optical, and bonding them together with your most advanced hybrid bonding technology.
That's right.
Some companies are saying we actually want all of that on the same chip. Is that something,
it's difficult to mix a photonic feature and the advanced electronic die.
Right.
It's difficult to do a monolithic. I think by using our hybrid bonding technique, we achieve the kind of connectivity, power efficiency, almost like a monolithic, but same time allow us to optimize the electronic die and the photonic die separately. I think this is, you get the best of both sides of the world. Yeah.
You spoke about pluggable transceivers, for the networking, but obviously what we're talking about here is more about integrated photonics, direct die to die.
Into the package, yeah.
What about pluggable version of that?
The pluggable version today, actually, if you look at the data center today, the prevailing way to do this is using pluggable at the board level.
Yes.
So you convert from electron to photon at the board level. So in the future, you convert within die. So the signal coming out of the die already, you turn electron to photon.
Yeah.
So that's where you get the efficiency. Yeah.
But will that ever be pluggable?
It is a pluggable. The optical, the fiber plug into your die. Yeah.
But you don't want to take it out. You want to leave it in. If it's in, it's in. It's in. It'd be remiss if I didn't bring up the fact that I very recently went on a fab tour to see the latest and greatest from ASML, this sort of new High-NA next generation EUV technology. And the company who was there is Intel. They're very forthright in talking about this technology and the fact that they want to be the first to deploy it. If I have you on the channel, I just have to bring up the question. Because there are some, variable responses from TSMC or quotes in the press about where you guys stand on this sort of High-NA technology. Given what we've said about, industry leading and new packaging and manufacturing technologies, where are you standing on High-NA?
Well, maybe let's step back. Let's don't forget TSMC is the leader in terms of bringing EUV into a high volume manufacturing. Back to our 6 nanometer generation, we're the very first in the industry to bring EUV to a high volume manufacturing environment. I think we're still the leader today in terms of EUV, use of EUV and the production efficiency. I think our R&D team will continue to look at the the new EUV capability, including obviously High-NA EUV, and we're going to pick the right place to intercept our technology node. There are lots of factors you have to consider, right? There is obviously the scalability factor. There is also a cost manufacturability factor. So I trust our R&D team will make the best decision where to choose the next generation EUV to intercept our future technology. Yeah.
And I guess on that front as well, there are also discussions about expanding worldwide production, trying to keep it more distributed rather than the single area in Asia. You guys have announced multiple fabs around the world. How's that progressing?
It's progressing very well and very fast too. If you look at our manufacturing footprint, it has expanded quite significantly just over the last few years. Obviously, you see we are expanding quickly in Arizona side, right? We built the first fab focusing on 4 nanometer, which we're going to production next year. And then we are building the second fab there, and also we announced phase 3, the third fab there. So we're going to continue to bring the most leading node, advanced node to North America. That's where our largest customer base, right, from 4 nanometer to 3 nanometer, down to 2 nanometer or even A16 in the future, right? So that's very exciting. At the same time, we're expanding our specialty technology in both Japan and here in Europe, right here in Europe, right? Japan, the Kumamoto project has gone very well. We're going to production, I believe, second half of this year. Yeah.
Oh, that's good.
Yeah. So we're going to bring most advanced MCU, embedded non-volatile memory, which is very important for auto industry here in Europe, to the heartland of the Eurozone. Yeah.
Does that extend to packaging in any way?
Packaging, we are evaluating option, but at the same time, I think right now we're working closely with our partner to bring up the capability, manufacturing capability in US, maybe in the future in other places. Yeah.
I guess one other topic I want to bring up is, because we're speaking about AI and machine learning, right? This crazy high demand. Are you seeing that TSMC or through your customers that the R&D is pivoting more to catering to those customers because they're in such high, they're so demanding. They want it all tomorrow, right?
Well, I think yes, AI is becoming, I think, one of the major technology platform where it consumes the most advanced silicon. But don't forget mobile. Mobile continue to be a large volume runner. And also mobile require most advanced technology. So we are addressing all the needs. We optimize technology for different applications, different segments. So our R&D work very closely with different customer, different applications. So I think this is something very exciting. We continue to drive our technology customization to address the future product needs.
So I mentioned that it's the symposium here in Europe. What conversations are you expecting to have today and tomorrow? Well, aside from me.
We want to hear our customers. We want to hear what they would need in the future for their product. Foundry business is very, very important to work closely with customers. We want to hear what customers' expectation and their product needs, and so we can develop the right technology to address our customer needs. Foundry business is a service business.
Right.
It's very, very important to connect, always stay connected with your customers. Yeah.
That's awesome. Well, good luck.
Sure. Thank you, Ian. It's a pleasure.
Thank you very much.
It's a pleasure
Thank
talking
you.
to you. Yeah.